Hello there and welcome to Napflix. I'm so glad you found your way here tonight. Maybe you've had a long day, or maybe you're just the kind of person who likes to fall asleep learning something extraordinary. Either way, you're in the right place. You've got nothing to do right now but rest. Let your breathing slow. Let the day fall away, because tonight, none of it matters. Tonight, we're going somewhere vast. We're drifting through the Milky Way, not the pale smear of light you see on a clear, dark night. That's barely a whisper of what's really there. Tonight, we're traveling through the whole thing. A structure so enormous that light itself takes 100,000 years to cross it. A spinning spiral of hundreds of billions of stars, ancient dust, invisible matter, and forces so powerful they have been shaping the universe since before the Earth existed. And beneath its beauty lie secrets that most people never hear. You'll hear tonight about a galaxy heading straight for us at 400,000 kilometers per hour, and why there is nothing anyone can do to stop it. You'll hear about the supermassive black hole sitting in silence at the center of everything. 4 million times the mass of the Sun, pulling stars around it so fast they complete an orbit in a decade. You'll hear about stars being flung out of the galaxy at 1 million kilometers per hour, never to return. About a substance that makes up most of the galaxy's mass that no human has ever seen, touched, or identified. About stars that are older than the galaxy itself. About the fact that every atom in your body was forged inside a star that exploded, and that the gold in every ring ever worn on Earth was made when two collapsed stars spiraled together and collided with a violence that briefly outshone the entire galaxy. Some of what you hear tonight may surprise you. Some of it may be the last thing you remember before you drift off. Either way, it will be here when you wake up. And just before we begin, if these calm, curious journeys help you unwind or give you a quiet way to end your day, I'd really appreciate it if you'd hit subscribe and leave a like on this video. It helps other sleepy souls find their way here too. One listener at a time. Now, let's begin. Right now, at this very moment, a galaxy is heading straight for us. It's called Andromeda, and it is enormous. 1 trillion stars, perhaps more, arranged in a spiral so wide that if you could see it clearly with the naked eye, it would appear 6 times larger than the full moon. On the clearest, darkest nights, far from any city, you can just about make it out. A faint smudge of light in the constellation that bears its name. It looks like nothing, a thumbprint on the sky. But that thumbprint is hurtling toward the Milky Way at roughly 400,000 kilometers per hour, and it has been doing so for billions of years. There is no force in the universe that will stop it. In about 4.5 billion years, Andromeda and the Milky Way will collide. Not in the way you might picture. There will be no cosmic crash, no sound, no explosion. Stars are so unimaginably far apart that when two galaxies pass through each other, almost nothing actually hits anything else. The average distance between stars in the Milky Way is about 4 light years, roughly 40 trillion kilometers. Even in the densest regions of both galaxies, the chance of two stars physically colliding during the merger is vanishingly small. It would be like throwing 2 handfuls of sand at each other from opposite ends of a football stadium. The grains would pass through without touching. Instead, it will be slow, gravitational, a dance that takes hundreds of millions of years to complete. The 2 spirals will stretch and distort, pulling long tidal tails of stars outward like taffy. They will pass through each other, swing apart, fall back together, and pass through each other again. Over and over, each pass drawing them closer, each time bleeding a little more momentum until eventually they settle. Merge, become one. Astronomers have already named it. The merged galaxy will be called Milkomeda, or sometimes Milkdromeda, which sounds faintly ridiculous for something so vast and permanent. But whatever we call it, it will no longer be a spiral. It will be an elliptical galaxy, a smooth golden cloud of old stars with no defined arms, no structure, no particular direction, just a quiet, enormous glow. The night sky from whatever remains of Earth, if Earth still exists, orbiting a sun that by then will be swelling into a red giant, will look nothing like the sky you see tonight. The familiar band of the Milky Way will be gone. In its place, a diffuse wash of light. A galaxy with no name we would recognize, built from the wreckage of two homes. But here is what makes this extraordinary rather than frightening. It has happened before. The Milky Way was not born whole. It was assembled piece by piece, collision by collision, over 13 billion years. And one of those collisions is happening right now, tonight, as you listen to this. There is a small galaxy called the Sagittarius Dwarf Elliptical Galaxy, a forgettable name for something that is being destroyed in real time. It sits on the far side of the Milky Way from us, and it is being pulled apart. Our galaxy's gravity has seized it, stretched it, and is currently unraveling it into long streams of stars that wrap around the Milky Way, like threads pulled from a jumper. These are called stellar streams, thin ribbons of stars that arc across the sky like faint scars, the stretched out remains of something that was once whole. They are among the most beautiful and haunting structures in the galaxy. Evidence of cosmic violence preserved in ribbons of ancient light. Over the next few 100 million years, the Sagittarius Dwarf will cease to exist as a separate thing. Its stars will become our stars. Its identity will dissolve into ours. And this is not unusual. Astronomers now believe the Milky Way has consumed dozens of smaller galaxies over its lifetime, possibly more. One especially significant meal, a galaxy now called Gaia Enceladus, was swallowed roughly 10 billion years ago, and it was large enough that the collision reshaped the entire structure of the early Milky Way. Many of the stars in our galaxy's outer halo, the vast spherical cloud of ancient stars that surrounds the visible disk, are not originally from here. They are immigrants, survivors of galaxies that no longer exist, still orbiting on paths that betray their foreign origin, tilted, elongated, moving against the flow. Some of these stars orbit backward, circling the galactic center in the opposite direction to everything else around them. Their reversed motion is a quiet signature of their origins, a gravitational memory of worlds that were torn apart billions of years ago. The Milky Way is not a pristine creation. It is a composite, a patchwork stitched together from the remains of smaller worlds, held in place by gravity and time, still growing, still hungry, still pulling things in. And at the very center of all of this, at the heart of the spiral, behind curtains of dust so thick that no visible light escapes, there is something extraordinary. It is called Sagittarius A star, and it is a black hole. Not just any black hole, a supermassive black hole, 4 million times the mass of the Sun, compressed into a space smaller than the orbit of Mercury around our own star. If you could somehow stand near it, which you cannot, because the gravitational forces would stretch you into a thread of atoms long before you arrived, you would see stars whipping around it at thousands of kilometers per second, completing full orbits in just a few years. Stars that take our Sun 225 million years to orbit the galaxy are, near Sagittarius A star, completing laps in a decade. One star, called S2, has been tracked for over 20 years as it loops around the black hole in an elongated orbit, reaching speeds of nearly 25 million kilometers per hour at its closest approach. That is roughly 3% of the speed of light. a star moving at 3% of the speed of light, dragged around by something that emits no light at all. We have never seen the black hole directly. No one has. A black hole, by definition, emits no light. But we have watched what happens around it. We have tracked individual stars as they swing past it, measured their acceleration, calculated the mass that must be pulling them. The scientists who did this work, Andrea Ghez and Reinhard Genzel, shared the Nobel Prize in Physics in 2020 for proving that a supermassive black hole sits at the heart of the Milky Way. They proved it not by seeing it, but by watching everything around it obey something invisible. In 2019, the Event Horizon Telescope, not a single telescope, but a network of radio dishes spanning the entire planet, linked together to create a virtual telescope the size of Earth, produced the first image of a black hole's shadow. Not Sagittarius A star, but a much larger one in a distant galaxy called M87. The image was extraordinary, a ring of superheated gas glowing around a dark void. The shadow of an event horizon, the boundary beyond which nothing, not light, not information, not time as we understand it, can return. 3 years later, they turned their combined telescopes toward our own galactic center and captured Sagittarius A star, a smaller, more turbulent ring around a smaller, more restless void, the shadow of the thing at the center of everything. For now, Sagittarius A star is quiet. It is not actively feeding. It is not consuming stars or gas at any dramatic rate. It sits there, patient and enormous, exerting its influence through gravity alone. But it was not always this way. There is evidence in the form of colossal structures called the Fermi bubbles, vast lobes of gamma-ray energy extending tens of thousands of light-years above and below the galactic plane. That Sagittarius A star once roared. Millions of years ago, something fell into it. A cloud of gas, a star, perhaps a cluster of material funneled inward by the galaxy's central bar. Whatever it was, it caused an eruption so powerful that it blew twin bubbles of high-energy radiation out of the galaxy's core, punching through the disk and inflating into the halo like enormous balloons of invisible fire. These bubbles are still there, still glowing in gamma rays, still expanding. You cannot see them with your eyes, but they are above you and below you right now, stretching across a significant fraction of the sky. Remnants of a tantrum thrown by a sleeping giant millions of years before humans existed. If the Milky Way once burned like a quasar, and there is growing evidence that it may have, then our quiet, familiar galaxy was once one of the brightest objects in the observable universe. A spiral wrapped around a blinding heart of light. That time has passed, but the echoes remain, written in gamma rays across the sky. And this is the thing about the center of the Milky Way that is hardest to hold in your mind. It is simultaneously the most violent place in the galaxy and the most gravitationally ordered. Stars near the core move with extraordinary precision. Their orbits are clean, predictable, almost musical. The black hole does not destroy randomly. It organizes, it conducts, it pulls everything into a slow, relentless choreography that has been playing out for billions of years. You are 26,000 light-years from this black hole. That is a comfortable distance. Comfortable enough that its gravity has no meaningful effect on your daily life, your orbit around the sun, or the glass of water on your bedside table. But it is there. It has always been there. And everything in the galaxy, every star, every cloud of gas, every planet, every atom of every living thing, orbits around it, whether they know it or not, including you. Right now, as you lie here, you are moving at 828,000 kilometers per hour around the center of the Milky Way. You don't feel it, just as you don't feel the Earth spinning or the Earth orbiting the Sun. But you are moving, fast, carried along by the Sun, which is carried along by the disk, which is carried along by gravity, which is anchored at its deepest point to a 4 million solar mass black hole sitting in the dark behind a wall of dust, silent and still and impossibly heavy. And it will still be there long after you fall asleep. Batch 2. Here is something that should unsettle you just slightly before you drift off. You can see almost none of the galaxy you live in. On the clearest, darkest night, far from any streetlight, any city, any trace of human glow. You might see a few thousand stars with the naked eye. On an exceptional night, perhaps 5,000. It feels like a lot. It feels like the sky is crowded with light. But the Milky Way contains somewhere between 100 billion and 400 billion stars. What you can see, even on the best night of your life, is roughly 0.0000003% of the total. Less than a rounding error, less than a speck of dust on a beach. And here is the thing that makes it worse. You are not even seeing the sky as it is. You are seeing the sky as it was. Light takes time to travel. The star Sirius, the brightest in the night sky, is about 8.5 light years away. When you look at it, you are seeing light that left that star 8.5 years ago. The star Betelgeuse, the red shoulder of Orion, is roughly 700 light years distant. The light reaching your eyes tonight left that star during the Middle Ages. Some of the faintest stars visible to the naked eye are thousands of light years away. Their light began traveling toward you before the Roman Empire existed. You are not looking at the sky. You are looking at the past. Thousands of different pasts, all arriving at your eyes at the same moment from thousands of different distances, each one a window into a different time. And that is only what you can see. The pale river of light that crosses the sky on a moonless night, the thing that gives the galaxy its name, is just the glow of the nearest portion of the disk seen edge on. Behind it, in every direction, billions upon billions of stars remain hidden. Some are too faint, some are too far away. And many, an extraordinary number, are blocked from view by vast clouds of interstellar dust that hang between the stars like curtains drawn across a window. These dust clouds are not empty space. They are structures made of microscopic grains of carbon and silicate, each one smaller than a grain of sand, forged in the outer layers of dying stars and expelled into space. They drift through the galaxy in vast clouds and tendrils, some stretching for hundreds of light years, dense enough to completely absorb the light of everything behind them. When you look at the Milky Way on a dark night, you might notice dark patches, rifts and lanes running through the bright band. Those are not gaps where stars are missing. Those are clouds of dust sitting between you and the stars behind them, swallowing the light before it reaches your eyes. The Great Rift, the dark band that appears to split the Milky Way in two, is one of these. It is not a division in the galaxy. It is a shadow, a wall of tiny grains collectively blocking the light of billions of stars. But the dust is not just an obstacle, it is an ingredient. These microscopic grains play a crucial role in the formation of new stars. They help gas clouds cool by radiating away heat. They provide surfaces on which hydrogen atoms can meet and form molecules. They shield the interiors of collapsing clouds from the radiation that would otherwise tear them apart. Without dust, the galaxy would form far fewer stars. The very thing that hides the galaxy from our eyes is part of what keeps it alive. And within that dust, scientists have found something unexpected. Complex organic molecules, carbon-based compounds that form the raw ingredients for life. Polycyclic aromatic hydrocarbons, simple sugars, alcohols, amino acid precursors. These are not living things, but they are the chemistry from which living things are built. They form in the atmospheres of dying stars, or within cold clouds shaped by radiation, and they drift through the galaxy on grains of dust, carried across light years by stellar winds. Some of this material settled into the cloud of gas that formed our solar system. Some of it fell onto the early Earth. The dust between the stars is not just debris, it is cargo, a delivery system for the chemistry of life, drifting silently through the dark. And this is only what we cannot see in visible light. The galaxy is radiating in wavelengths our eyes were never built to detect. X-rays pour from the regions around black holes and collapsed stars. Radio waves drift from cold hydrogen gas, from pulsars, from the faint magnetic breath of the interstellar medium. Gamma rays shimmer from the Fermi bubbles and the remnants of ancient supernovae. Infrared light, the only wavelength that can penetrate the dust, reveals the dense, glowing heart of the galaxy that is completely invisible to the naked eye. The galaxy is also threaded with an invisible magnetic field. It is weak by earthly standards, tens of thousands of times weaker than a refrigerator magnet, but it stretches across the entire disk, rises into the halo, and weaves through every cloud and stream of gas in the interstellar medium. This field shapes how cosmic rays travel. It influences how gas clouds collapse into stars. It guides the motion of charged particles and aligns the dust grains that polarize the light passing through them. The Milky Way does not just glow with light, it hums with magnetism, a subtle, invisible pulse running through its bones, detectable only with radio telescopes and careful analysis, but woven into the structure of everything. Every second, cosmic rays pass through your body. High-energy particles, mostly protons launched by exploding stars, streaming through the galaxy at close to the speed of light, bending through magnetic fields, bouncing off clouds and passing through you as if you weren't there. You cannot feel them. You will never feel them. But they are constant. They carry information from places we cannot see, from stellar cores, from collapsing giants, from the galaxy's most violent events. They are the shrapnel of ancient explosions, still ricocheting through the galaxy billions of years later. And then there are the neutrinos. Trillions of them pass through your body every second, produced in the nuclear furnaces of stars. They are so light and so weakly interacting that they could travel through a wall of lead a light year thick, and most of them would come out the other side. Special observatories buried deep underground or encased in Antarctic ice, like the ice cube detector at the South Pole, try to catch just a few flashes of light from a rare collision between a neutrino and an atom of ice. Each detection is a message from a distant star, decoded in the dark beneath a frozen continent. The galaxy is whispering in particles, in silence, in lightless rays. And even as you rest, it has not stopped. You live inside an ocean of invisible light. But the invisible radiation is not even the strangest part. The strangest part, the part that has kept physicists awake at night for decades, is what happens when you try to weigh the galaxy. It does not add up. If you take every star in the Milky Way, every cloud of gas, every grain of dust, every planet, every black hole, every neutron star, every scrap of matter you can detect or reasonably infer, and you add it all together, you get a number. And that number is not nearly enough. Not nearly enough to explain how fast the outer stars are moving. Here is the problem. In any gravitational system, things farther from the center should orbit more slowly. This is how the solar system works. Mercury races around the Sun. Neptune crawls. The further out you go, the weaker the gravitational pull and the slower the orbit. This is basic Newtonian physics. It has worked for centuries, but in the Milky Way, it doesn't work. Stars in the outer regions of the galaxy are orbiting almost as fast as stars near the center. They should not be doing this. Based on the amount of visible matter, they should be moving much more slowly, or they should have been flung out of the galaxy entirely, scattered into intergalactic space like sparks from a wheel. The galaxy, by all rights, should not hold together, and yet it does. The answer, or at least the best answer anyone has, is dark matter. An invisible substance that does not emit light, does not reflect light, does not absorb light, does not interact with ordinary matter in any way that we can detect, except through gravity. And there is a lot of it. Current estimates suggest that dark matter outweighs all the visible matter in the galaxy by a factor of roughly 6 to 1. Some estimates put it higher. The Milky Way is not mostly stars. It is not mostly gas. It is not mostly dust. It is mostly something we have never seen. The dark matter is not concentrated in the disk. It forms a halo, an enormous, roughly spherical cloud that extends far beyond the visible galaxy, perhaps 3 or 4 times the diameter of the starry disk. This halo is invisible. Completely invisible. No telescope has ever imaged it. No instrument has ever directly detected a single particle of dark matter. We know it is there only because of what it does to everything else. It holds the galaxy together. It determines how fast stars orbit. It shapes the way smaller galaxies fall inward and are consumed. It is the scaffolding upon which the entire visible structure is built. And within this halo, the majority of the Milky Way's mass resides. When we think of the galaxy, we picture its spiral arms and starry plane, but that is only the glowing surface. The mass that defines the galaxy, its gravity, its motion, its reach, is mostly hidden, enveloping everything like a quiet shroud. There is more mass outside the visible disk than inside it. The galaxy you can see is the smaller part of the galaxy that exists, and no one knows what it is. This is not a small gap in our knowledge. This is not a minor detail awaiting confirmation. The majority of the mass of the galaxy you live in, the galaxy that contains your sun, your planet, your body, every atom of every person who has ever lived, is made of something that, as of this moment in human history, we cannot identify. We can describe what it does. We can model its effects. We can tell you where it must be and roughly how much of it there is. But we cannot tell you what it is. Not yet. Laboratories around the world are trying. Detectors buried deep in mountains, shielded from cosmic rays, sit in the dark, waiting for a single particle of dark matter to bump into an atom of xenon or germanium. So far, nothing. The search continues. The silence continues. The woman who proved this was real, who provided some of the most compelling evidence that dark matter existed, was an astronomer named Vera Rubin. In the 1970s, working at the Carnegie Institution in Washington, Rubin measured the rotation speeds of stars in dozens of spiral galaxies, including our own. What she found was the same thing, over and over. The outer stars were moving too fast. The rotation curves were flat where they should have been declining. Something unseen was providing extra gravity. Something massive and invisible was holding the galaxies together. Her results were initially met with skepticism. Some physicists suggested the laws of gravity themselves might be wrong at galactic scales. Others simply ignored her. She was a woman working in a field dominated by men, at a time when women were not always welcome at major observatories. She had been discouraged from pursuing astronomy as an undergraduate. When she arrived at Palomar Observatory in California to observe, she was told there were no women's bathrooms in the building. She drew a small figure of a woman and taped it to the door of the men's room. She was, at various points in her career, the only woman in the room. She kept working anyway. Her data was meticulous. Her observations were repeated and confirmed. And over time, the scientific community came to accept what she had shown, that most of the universe is made of something we cannot see. It was one of the most important discoveries in the history of astronomy. Vera Rubin was never awarded the Nobel Prize. She died in 2016 at the age of 88. The dark matter she helped reveal is still unexplained, but the evidence she gathered changed everything. The galaxy we thought we understood, a structure of stars and gas and dust governed by visible forces, turned out to be a thin, luminous skin stretched over a vast, invisible body. And that invisible body holds everything in place. So here is where you are tonight, as you lie in the dark. You are inside a galaxy that is mostly invisible. Most of its mass is something no one can identify. Most of its light is in wavelengths you cannot see. Most of its stars are hidden behind dust. The dust itself carries the building blocks of life. A magnetic field you cannot feel threads through every part of it. Particles from ancient explosions are streaming through your body at close to the speed of light, and you cannot feel a single one of them. The galaxy is not what it looks like. It has never been what it looks like. What you see on a dark night, that beautiful pale river of light, is the thinnest, faintest fraction of what is actually there. A whisper from a structure so vast and so strange that even after centuries of study, we are still standing at the edge of it, squinting into the dark, trying to work out what we are part of. And the dark matter holds it all in place. Invisible, patient, and absolute. Without it, every star in the galaxy, including the one keeping you alive, would fly apart and scatter into nothing. It will not do that tonight. Centuries. Galactic time. The sun, our star, is orbiting the center of the Milky Way. You already know this. But what you may not know is how long that orbit takes. At 828,000 kilometers per hour, a speed so fast that if you could travel at it, you would reach the moon in less than 30 minutes. The sun still takes approximately 225 million years to complete a single lap of the galaxy. 225 million years. That is one galactic year. Let that settle for a moment. A single orbit, one trip around, and in the entire lifetime of the sun, 4.5 billion years of burning, of holding its planets in place, of warming the Earth just enough for water to remain liquid and life to crawl out of the ocean. The sun has completed roughly 20 of these orbits. 20 laps, that is all. The last time the solar system was in this part of the galaxy, the last time it occupied roughly the position it sits in now, the supercontinent Pangaea had just begun to break apart. Dinosaurs had not yet appeared. The Atlantic Ocean did not exist. The Himalayas had not risen. The entire history of complex life on land. Every dinosaur, every mammal, every bird, every flowering plant, every human civilization has unfolded within a single galactic year. And during that orbit, the sun has not followed a perfectly flat path. It bobs. As it circles the galactic center, it drifts gently above and below the plane of the disk, like a cork on a slow, invisible wave. Rising and falling over tens of millions of years, pulled up and then drawn back down by the gravitational tug of the galaxy's mass. The amplitude is not enormous, perhaps 100 light years above the plane, then 100 below, but it is constant. a slow vertical oscillation layered on top of the already vast horizontal orbit. Some researchers have wondered whether this bobbing motion might correlate with periods of increased comet impacts or mass extinctions on Earth, as the solar system passes through denser regions of the disk, where gravitational disturbances could nudge objects in the outer solar system inward. The evidence is not conclusive, but the motion is real. Even on its steady path around the center, the Sun is not gliding. It is swaying softly through space, and here is the part that unsettles. The stars you see in the sky tonight were not the stars overhead when the dinosaurs looked up. The solar system has moved. The stars around us have moved. Everything is in motion, always, drifting through the galaxy on overlapping orbits at different speeds, shuffling and rearranging like cards in an infinitely slow deck. The constellations you learned as a child did not exist a million years ago and will not exist a million years from now. They are a temporary arrangement, a momentary pattern. The stars that form Orion's belt are not even close to each other. They just happen from our current position in the galaxy at this particular moment in time to line up. Mintaka, the rightmost star, is roughly 380 light-years away. Alnilam, the middle star, is over 1,000. They are separated by hundreds of light-years of empty space, but from here to night, they appear to sit side by side. A trick of perspective, a coincidence of angle, nothing more, nothing in the sky is fixed. It only looks that way because human life is so short. And while everything drifts, most of it drifts gently. Stars orbit the galactic, center pulled along by gravity, moving at speeds that are extraordinary by human standards but entirely routine by galactic ones. Most stars live their entire lives, billions of years, within the same broad region of the galaxy, following long, slow, predictable paths. But not all of them. Some stars wander far from where they were born. A star's birthplace does not always define its destiny. Over time, many stars drift away from their natal clouds, pushed by gravitational interactions with other stars, by orbital resonances with the spiral arms, or by the slow pull of the galactic bar. Some migrate gradually, shifting their orbits inward or outward as they spiral through the galaxy over hundreds of millions of years. Even our Sun is probably not where it began. Some astronomers believe the Sun formed closer to the galactic center, in a denser, more metal-rich region, and has since migrated outward to its current orbit. Its birth cluster, the group of sibling stars formed from the same collapsing cloud, dissolved long ago, its members scattered across the galaxy, flung into different orbits by time and gravity. They may still be out there, stars with the same chemical fingerprint as the Sun, the same age, the same origin, now shining in completely different parts of the sky, unrecognizable, lost among billions. Astronomers are searching for them. Using data from the Gaia spacecraft and spectroscopic surveys that can measure the chemical composition of individual stars, they hope to identify the Sun's long-lost siblings. Stars that share its birthday but took different paths through the galaxy. A few candidates have emerged, but the search is painstaking. The galaxy is vast, and the Sun's family was scattered billions of years ago. Home for a star may only be temporary, but not all wanderers drift gently. Some stars are moving far too fast, and they are heading in the wrong direction. These are called hypervelocity stars, and they are among the strangest objects in the Milky Way. They are not drifting, they are not orbiting, they are fleeing. Moving at speeds of over 1 million kilometres per hour, fast enough to escape the gravitational pull of the entire galaxy, they are being flung outward, away from the disk, away from the spiral arms, away from everything, into the void between galaxies. Most of them were made this way by the supermassive black hole. The mechanism is violent and elegant. Imagine a binary star system, two stars orbiting each other, bound by mutual gravity, drifting too close to Sagittarius A star. The black hole's gravity seizes the pair and tears them apart. One star is captured, pulled into a tight orbit around the black hole, or consumed entirely. The other star, released from its partner and catapulted by the same gravitational interaction, is flung outward at extraordinary speed, slingshot by a 4 million solar mass anchor, hurled into the dark with enough velocity to leave the galaxy entirely. But the black hole is not the only thing that can produce these runaways. Binary stars can be torn apart by tidal forces in the dense cores of globular clusters, where stars are packed thousands of times more closely together than in our neighborhood. When a massive star in a tight binary explodes as a supernova, the surviving companion can be released at enormous speed suddenly, unshackled from its partner's gravity. And three-body encounters, chaotic gravitational dances between three stars passing too close, can slingshot one member outward while the other two settle into a tighter orbit. The galaxy has many ways of throwing things away. These rogue stars travel alone, far above or below the galactic plane, moving through the halo or already beyond it, glowing faintly in the dark, like embers thrown from a fire. They will never orbit anything again. They will never be part of a system again. They are leaving permanently, carrying the light and chemistry of the Milky Way into intergalactic space. Tiny lighthouses drifting far beyond the spiral's edge. They carry the galaxy's memory outward, becoming solitary pilgrims in the great dark between galaxies. Astronomers have found several dozen of them so far. There are almost certainly many more. And the stars are not the only things out there drifting alone. There are planets too. Billions of them. Worlds with no star, no sun, no warmth except whatever heat remains trapped in their cores from the moment of their formation. These are called rogue planets, and recent estimates suggest there may be more of them in the Milky Way than there are stars. Think about that for a moment. More planets wandering alone in the dark than there are suns to light them. Some were formed normally, born in the disk of gas and dust around a young star, assembled from the same material as their siblings. And then ejected. Gravitational interactions with other planets, close encounters with passing stars, the chaotic dynamics of young solar systems. All of these can fling a planet out of its orbit and into the galaxy at large. Others may have formed independently, condensing directly from collapsing gas clouds, never orbiting anything at all. They are extraordinarily difficult to detect. They emit no light. They reflect nothing. The only way to find them is through gravitational microlensing, the fleeting distortion of background starlight as an unseen mass passes in front of it. As a rogue planet drifts between us and a distant star, its gravity bends the star's light just slightly, causing the star to brighten briefly and then fade. These events last hours or days, they never repeat, and they require monitoring millions of stars simultaneously to catch even a few. But the detections are real, and the numbers they imply are staggering. In 2023, the James Webb Space Telescope discovered pairs of rogue planets drifting together through the Orion Nebula. Objects too small to be stars, unbound to any solar system, yet orbiting each other in the cold. They were given the name jumbos, Jupiter mass binary objects. And no one is entirely sure how they formed. They challenge existing models of planet formation. They are something new, something the galaxy produced that we did not predict. The galaxy is full of dark, wandering worlds, cold, silent. drifting through the space between stars on journeys that will last billions of years, with no destination and no companion. Some of them may be Earth-sized. Some may be larger than Jupiter. Some may have thick atmospheres that trap enough internal heat to keep a surface above freezing, or subsurface oceans warmed by radioactive decay. Whether any of them harbor life is a question no one can answer yet, but they are out there, right now, in numbers that dwarf the planets we can see. And then there are the stars that should not exist at all. In the outermost reaches of the galaxy, drifting through the halo far above the plane of the disk, astronomers have found stars that appear to be older than the Milky Way itself. Not by a little, by a lot. These are ancient, metal-poor stars. Their atmospheres contain almost no elements heavier than helium, which means they were born before generations of supernovae had enriched the cosmos with iron, calcium, carbon, and gold. They formed when the universe was still young, still raw, still learning to make complicated things. In astronomy, the word metal does not mean what it means in everyday life. It means any element heavier than helium. Carbon is a metal. Oxygen is a metal. Iron, obviously, is a metal. The earlier stars had almost none of these because they formed before earlier generations of stars had a chance to forge and scatter them. These primordial stars, the very first generation, sometimes called population 3 stars, are believed to have been enormous, hundreds of times the mass of the Sun, burning hot and fast and dying young in catastrophic explosions that seeded the universe with its first heavy elements. No population 3 star has ever been directly observed. They burned out billions of years ago. But the stars that formed immediately after them, from the faintly enriched gas they left behind, are still here, still burning. The second generation, the children of the first light. Some of these stars may have been born more than 13 billion years ago, in the first few 100 million years after the Big Bang. That places their birth before the Milky Way had fully assembled, before the disk had formed, before the spiral arms existed. They were not born here. They were born in the small primordial galaxies that later merged to become the Milky Way. Tiny, chaotic clumps of gas and dark matter that collapsed under their own gravity in the earliest epoch of the universe and ignited the first generation of stars. Those first galaxies no longer exist. They were consumed, pulled apart and absorbed into the growing Milky Way over billions of years, their stars scattered into the halo, their identities erased. But the stars themselves survived. They are still burning, faintly, slowly, with a soft red glow. Low-mass stars that burn their hydrogen so conservatively that they can last for tens of billions of years, far longer than the current age of the universe. They are the oldest living things in the galaxy. Not living in the biological sense, but burning, still fusing, still shining. Relics from a time before the galaxy they now inhabit had taken shape. They orbit in long, tilted, eccentric paths that bear no resemblance to the neat, circular orbits of the disk. Their motion is a record of their origin, a gravitational memory of the smaller, wilder galaxies they came from. Galaxies that were torn apart so long ago that nothing remains of them except these few, ancient, patiently burning stars. One of them, a star catalogued as HD 140283, sometimes called the Methuselah star, has been estimated at close to 14 billion years old. The universe itself is only 13.8 billion years old. The margin of error in the measurement is just large enough to keep things consistent, but only barely. It is, by any accounting, one of the oldest objects ever found. A star that was already ancient when the Earth was born. when the sun ignited, when the Milky Way's disk settled into its current shape. It is still there tonight, still burning. A tiny, faint point of light in the constellation Libra, visible with a small telescope if you know exactly where to look. It moves quickly for a star. Its high velocity across the sky was one of the first things astronomers noticed about it, a sign of its halo orbit, a signature of its foreign, ancient origin. Most people will never see it. Most people have never heard of it. But it has been shining since before almost anything in the galaxy existed, and it will go on shining long after our sun has died. The galaxy is full of things like this. Things that are older than they should be, faster than they should be, darker than they should be, lonelier than they should be. Stars that predate their own galaxy, planets that orbit nothing, rogue suns racing toward intergalactic space. And all of it turning, drifting, orbiting in galactic time, with a patience that makes human history feel like the blink of an eye. Because it is. One galactic year contains the rise and fall of every civilization that has ever existed on Earth, and the galaxy has completed billions of them. We have been here for a fraction of one, and still, the galaxy turns. The spiral arms of the Milky Way are not real. That is not quite the right way to say it, but it is close enough to be worth sitting with for a moment. The beautiful, sweeping arms that give the galaxy its shape, the features that make it look, in every artist's impression, like a vast spinning pinwheel, are not solid structures. They are not rivers of stars flowing outward from the center. They are not fixed. They are not permanent. They are, in the most precise sense, an illusion. A very convincing, very beautiful, very persistent illusion. But an illusion nonetheless. What the spiral arms actually are is density waves, patterns of compression that move through the galactic disk like ripples moving across the surface of a pond. As a wave passes through a region of space, it compresses the gas and dust that is already there, squeezing it together until it collapses under its own gravity and ignites into new stars. These newborn stars are hot, bright and blue-white, and they light up the region of compression like a torch. They are the reason the arms appear to glow. But the stars themselves do not stay in the arm. They drift through it, born on one side and emerging on the other, while the wave itself moves on at a different speed, compressing new material and creating new stars in its wake. Think of it as a traffic jam on a motorway. The jam itself stays in roughly the same place, but the individual cars pass through it. They slow down as they enter, bunch together, and then speed up again as they exit. The jam is a pattern, not a collection. The spiral arms work the same way. The stars that light them up right now are not the same stars that lit them up 100 million years ago, and they will not be the same stars 100 million years from now. The arms are self-sustaining patterns of creation, rolling through the disk, endlessly forming and discarding the bright young stars that make them visible. And here is the eerie detail. Many of the brightest stars in the arms will never leave them. Massive, luminous stars, the blue supergiants that make the arms so striking, burn through their fuel in just a few million years. They are born inside the density wave, shine briefly with extraordinary intensity, and then explode as supernovae before they ever drift out the other side. The arms are lit by stars that live and die within them. A rolling wave of birth and death and birth again, cycling through the disk for billions of years. Those supernovae are not just endings, they are engines. When a massive star explodes, the shock wave rips outward through the surrounding gas at thousands of kilometers per second. It compresses nearby clouds, triggering them to collapse and form new stars. It carves vast cavities in the interstellar medium, bubbles of superheated gas, hundreds of light years across, that glow in X-rays and slowly expand into the surrounding space. Sometimes multiple supernovae go off in the same region within a few million years, their combined shockwaves punching through the galactic disk entirely, creating towering chimneys of hot gas that vent upward into the halo. The galaxy breathes through these chimneys. Energy, gas, and magnetic fields escape from the plane of the disk and rise into the dark above, carrying heavy elements forged in the hearts of dying stars up and out of the crowded stellar neighborhoods where they were born. And the supernovae leave things behind, not just gas and dust and newly forged elements, but remnants, collapsed objects of extraordinary density. When a star between roughly 8 and 25 times the mass of the Sun explodes, its core does not disappear. It collapses into a neutron star, an object roughly 20 kilometers across, but containing more mass than the Sun. The density is beyond comprehension. A sugar cube-sized piece of neutron star material would weigh roughly 1 billion tons. The gravity at the surface is so intense that the tallest mountains are measured in millimeters. The object is essentially one enormous atomic nucleus, held together by gravity and the quantum pressure of neutrons, packed as tightly as physics allows. And many of these neutron stars spin fast. Some rotate hundreds of times per second, sweeping beams of radiation across space like cosmic lighthouses. These are pulsars, and they are among the most precise natural clocks in the universe. Their pulses are so regular, so extraordinarily, almost impossibly regular, that when the first pulsar was discovered in 1967 by a graduate student named Jocelyn Bell Burnell, the signal was initially labeled LGM1, Little Green Men. Because the regularity seemed too perfect to be natural, it seemed artificial. It seemed like a signal from an intelligent civilization. It was not. It was a dead star spinning in the dark, sweeping a beam of radio waves across the galaxy with the precision of a Swiss watch. Bell Burnell's supervisor, Anthony Hewish, received the Nobel Prize for the discovery. Bell Burnell did not. The pattern, you may notice, repeats. Today, astronomers have catalogued thousands of pulsars across the Milky Way. Some spin once every few seconds. Others spin hundreds of times per second. Millisecond pulsars, spun up by stealing material from a companion star, rotating so fast that their equators move at a significant fraction of the speed of light. These millisecond pulsars are so stable that they are used as cosmic timekeepers, their signals monitored for tiny variations that could reveal passing gravitational waves. Ripples in the fabric of space-time itself, generated by merging black holes in distant galaxies. Arrays of pulsars spread across the Milky Way are being used right now as a galaxy-sized gravitational wave detector. The dead stars are listening for the vibrations of the universe, and they are beginning to hear them. From a great distance, the spiral arms look elegant and still, like a photograph. From inside, they are a slow-motion catastrophe of collapsing gas, igniting suns, detonating stars, collapsing remnants, and spinning pulsars, playing out across thousands of light years, never pausing, never finishing. And we do not even know how many arms there are. From our position inside the disk, the structure of our own galaxy is maddeningly difficult to map. Dust obscures the view. Stars overlap. Distances are hard to measure precisely. For decades, the textbook answer was 4 major arms. Then observations suggested 2 dominant arms with smaller spurs and fragments branching off. Some models show the arms splitting and reconnecting in ways that defy simple classification. The Milky Way may not be a grand design spiral at all. It may be something messier, more fractured, with arms that fade and reappear and twist in ways we cannot yet trace from the inside. We are trying to draw a map of a forest while standing in the middle of it, and the trees are moving. What we do know is that the galaxy has a bar. When astronomers look toward the galactic center in infrared light, which can penetrate the dust that blocks visible wavelengths, they see not a simple core of stars, but an elongated, thick stripe cutting across the middle of the galaxy like a bridge. This is the galactic bar, a dense rotating structure roughly 27,000 light-years long, composed of billions of old, reddish stars. About 2/3 of all spiral galaxies have bars, and the Milky Way is one of them. The bar rotates slowly, and its gravitational pull shapes the inner spiral arms, channels gas inward toward the center, and may funnel material toward the supermassive black hole. It is a dynamic engine sculpting the galaxy's heart from within. And inside the bar, the structure becomes even stranger. The central bulge, the thick concentration of stars at the galaxy's core, is not round. It is peanut-shaped. Seen from the side, it swells in the middle and narrows at the ends, like an hourglass made of 100 billion stars. This bizarre geometry formed over billions of years, as the bar buckled under its own internal dynamics. Stars in the center slowly puffing outward along vertical orbits, settling into a three-dimensional shape that no one predicted until it was observed. There are even hints of a second, smaller bar nested inside the first, tilted at a different angle, rotating independently. A bar within a bar, a layered, shifting labyrinth of light and motion at the heart of everything. What we also know is that our Sun sits in a relatively minor feature, a small structure called the Orion Spur, nestled between two larger arms, the Sagittarius Arm and the Perseus Arm. It is not a major arm. It is not especially dense or active. It is, by galactic standards, a quiet lane. And that may be exactly why we are here. In the dense inner regions of the galaxy, closer to the core, supernovae are more frequent. Radiation is more intense. Gravitational disruptions are more common. The environments are hostile to the kind of long-term stability that complex life seems to require. In the sparse outer regions, the galaxy is too thin, too metal-poor. There may not be enough heavy elements to form rocky planets like Earth. But in between, in a band that astronomers sometimes call the galactic habitable zone, conditions may be just right. Moderate star density, enough heavy elements to build planets, enough distance from the core to avoid the worst of the radiation, and near what is called the corrotation radius, the distance from the center where stars orbit at roughly the same speed as the spiral arms themselves. A planet could avoid frequent crossings of those arms, reducing the risk of nearby supernovae. Our Sun orbits near this radius. Earth sits in a quiet spur in a moderate zone, at a resonant distance from the center, in a galaxy whose structure may have, by accident or by the quiet logic of physics, created a pocket of calm just stable enough for life to emerge. This is not proof of anything. It is not evidence of design. It is simply where we are, and it may explain, in part, why we are here to notice. Now, let's go deeper, into the substance of the galaxy itself. Every atom in your body was made inside a star. This is not a metaphor. It is not a poetic exaggeration. It is a literal, physical fact. The hydrogen in the water in your cells is primordial. It has existed since shortly after the Big Bang, nearly 14 billion years ago. But everything else, the carbon in your muscles, the calcium in your bones, the iron in your blood, the oxygen you are breathing right now, was manufactured inside a star through nuclear fusion at temperatures of millions of degrees over millions of years. When a star like the Sun reaches the end of its life, it swells into a red giant and sheds its outer layers into space in a slow, beautiful exhalation called a planetary nebula. A misleading name since it has nothing to do with planets. These shells of gas expand outward, glowing in greens and blues and reds as different elements are illuminated by the ultraviolet light of the exposed stellar core. They carry with them the elements the star spent billions of years forging: carbon, nitrogen, oxygen, releasing them into the interstellar medium, where they mix with existing gas and dust and eventually become part of new stars, new planets, new everything. The Milky Way recycles. Every generation of stars enriches the galaxy. The first stars had almost nothing but hydrogen and helium. When they died, they scattered the first carbon, the first oxygen, the first iron into space. The next generation of stars formed from this slightly enriched material, burned through it, and when they died, scattered even more, and so on. Generation after generation, each one leaving the galaxy a little richer, a little more complex, a little more capable of producing rocky planets and organic chemistry and, eventually, life. The atoms in your body have been through this cycle at least once. Some of them have been through it several times. Born in a star, scattered into space, gathered into a new star, scattered again, gathered into the cloud that formed the sun, and finally settling into the planet you are lying on. But the heaviest elements, iron, nickel, and beyond, require something more violent. They are forged in supernovae. When a massive star, 8 times the mass of the sun or more, exhausts its fuel, its core collapses in less than a second. The outer layers rebound off the collapsing core and are blown outward in an explosion so powerful that for a few weeks, a single dying star can outshine an entire galaxy. In that explosion, in that brief, cataclysmic instant, elements heavier than iron are created and scattered across space at thousands of kilometers per second. The silicon in the glass on your bedside table, the copper in the wires in your walls, the zinc in the coins in your pocket. All of it was forged in the final moments of a star that died before the sun was born, scattered into a cloud of gas that eventually collapsed and formed our solar system. But there is one more layer to this, and it is perhaps the most extraordinary of all. Gold, platinum, uranium. These elements are too heavy to be made in ordinary supernova. They require something rarer, something more violent, something so extreme that it was only confirmed in 2017. The collision of 2 neutron stars. A neutron star is what remains when a massive star explodes and its core collapses, but not quite far enough to become a black hole. It is an object roughly the size of a city, perhaps 20 kilometers across, but containing more mass than the sun. A single teaspoon of neutron star material would weigh about 1 billion tons. The density is beyond anything in normal experience. The gravity is so intense that the surface is smoothed to within a fraction of a millimeter. When 2 neutron stars orbit each other, they slowly spiral inward, losing energy through gravitational waves, ripples in the fabric of space-time itself. Over millions of years, they draw closer and closer, orbiting faster and faster until they collide. The result is called a kilonova, and it is one of the most violent events in the universe. In that collision, in a burst of energy that briefly outshines the entire galaxy, enormous quantities of the heaviest elements are forged: gold, platinum, uranium, thorium, created in a storm of neutrons so dense that atomic nuclei are built up layer by layer in fractions of a second through a process called rapid neutron capture, then hurled outward into space at a significant fraction of the speed of light. In August 2017, Gravitational wave detectors on Earth, the twin LIGO observatories in the United States, and the Virgo detector in Italy picked up a signal from two neutron stars merging in a galaxy 130 million light-years away. The signal was different from the black hole mergers they had detected before. It was longer, higher in frequency, and it ended with a distinctive chirp. Within seconds, a burst of gamma rays arrived from the same patch of sky. Telescopes around the world turned to watch. Over the following days and weeks, they observed a fading glow. The radioactive afterglow of newly forged heavy elements, decaying and cooling in the expanding debris cloud. The glow was rich in infrared, consistent with the production of vast quantities of gold and platinum. One estimate suggested the collision produced roughly 10 times the mass of the Earth in gold alone. 10 Earths worth of gold forged in seconds in the death spiral of two objects smaller than a city. Every gold ring ever worn, every platinum pendant, every trace of uranium deep in the Earth's crust. All of it was made this way, in the collision of dead stars in a flash of violence that lasted seconds, hundreds of millions of years before the Earth formed. The atoms found their way into a cloud of gas. The cloud collapsed. A new star ignited. Our sun. The leftover material formed a disk. The disk became planets. One of those planets cooled, formed oceans, and eventually produced a species capable of digging the gold out of the ground and putting it on their fingers. You are, in the most literal sense, made of dead stars. The calcium in your bones came from a supernova. The iron in your blood came from a dying giant. And the gold, if you are wearing any tonight, was forged in the collision of two neutron stars in a galaxy far from here, in an explosion that outshone 100 billion suns. The galaxy does not just contain you, it built you. Atom by atom, explosion by explosion, across billions of years. Every culture that has ever looked up at the night sky has seen the Milky Way, and every one of them has tried to explain it. The ancient Greeks saw it as a river of milk, spilled from the breast of the goddess Hera. The story goes that Zeus placed his infant son Heracles at Hera's breast while she slept, hoping the divine milk would make the child immortal. When Hera woke and pulled away, the milk sprayed across the heavens. The Greek word for milk is gala. From it, we get the word galaxy. Every time you say the word, you are repeating a story that is more than 2,000 years old. But the Greeks were not alone in seeing something liquid in the sky. The Hindi name for the Milky Way is Akash Ganga, the Ganges of the sky. A celestial river, sacred and eternal, mirroring the holy river on Earth. In Chinese tradition, it is the Silver River, Yin He, and it is the setting for one of the oldest love stories in East Asian culture, the tale of the weaver girl and the cowherd, two lovers separated by the celestial river, permitted to meet only once a year when magpies form a bridge across the stars. The festival of Chikshi, still celebrated today, marks this annual reunion. The weaver girl is the star Vega. The cowherd is Altair. The river between them is the Milky Way. And every summer, when those two bright stars shine on opposite sides of the pale band overhead, the story is being told again, in light, whether anyone remembers the words or not. The Norse saw it differently. To them, the band of light was the path to Valhalla, the road walked by fallen warriors on their way to the Hall of the Gods. In some tellings, it was called the Winter Way, a frost bridge across the heavens, glowing faintly in the long Scandinavian dark. In Finnish tradition, it was Linnunrata, the bird path, the route that migratory birds followed between the living world and the land of the dead. The Cherokee called it Gi Li Ut Sun, Stan Un Yi, Where the Dog Ran, and told a story of a great dog that stole cornmeal from a mill and spilled it across the sky as it fled. The Khoisan people of southern Africa saw it as the embers of a fire, thrown into the sky by a girl who wanted to create a path of light so people could see their way home at night. The Aboriginal Australians, whose astronomical traditions are among the oldest continuous knowledge systems on Earth, stretching back at least 65,000 years, saw not just the light of the Milky Way, but also the darkness. The dark patches, the dust lanes, the rifts and shadows that run through the bright band. Where European astronomers saw absence, Aboriginal astronomers saw presence. The dark spaces formed figures, the emu in the sky, a vast shape stretching across the southern Milky Way, its head the dark Coalsack Nebula near the Southern Cross, its neck and body traced by the dark lanes running toward the Galactic center. The emu's position in the sky told communities when to gather eggs, when to hunt, when seasons were changing. It was practical astronomy, read not in stars but in the shadows between them. When the emu appeared to be running, its legs stretched behind it. That was the season to collect emu eggs. When it appeared to be sitting, the emus were nesting and should not be disturbed. The same dust clouds that modern astronomers study to understand star formation, Aboriginal Australians had been reading as a seasonal calendar for tens of thousands of years. And the Inca, in the mountains of South America, developed a remarkably similar tradition, independently, on the opposite side of the Pacific. They called the dark patches Yana Fuyu, dark clouds, and saw in them animals, a llama and her calf, a fox, a toad, a serpent, a partridge. These dark constellations were as important to Inca astronomy as the bright constellations were to the Greeks. They mapped the sky not by its light alone, but by its darkness. The llama constellation was directly linked to animal husbandry. Its appearance in the sky governed when llamas were bred, when they gave birth, when they were shorn. Two civilizations separated by the entire Pacific Ocean. With no contact between them, both looked at the dark spaces in the Milky Way and saw animals. Both built calendars from the shadows. Every one of these cultures was looking at the same thing, the same band of light, produced by the same billions of stars viewed from the same planet. But what they saw, what they made of it, was shaped entirely by where they lived, what they knew, and what they needed from the sky. The Milky Way is not just a galaxy, it is a mirror. It reflects back whatever the observer brings to it. The scientific story of the Milky Way begins much later, and it begins with not knowing what it was. For most of human history, no one understood that the pale band in the sky was made of stars. It was Galileo Galilei in 1610 who first turned a telescope toward it and saw what no human eye had ever resolved. The band was not a cloud or a mist or a river. It was stars, thousands upon thousands of them, packed so closely together that to the naked eye they blurred into a single glow. His telescope was crude by modern standards. A simple tube with two lenses, magnifying perhaps 20 or 30 times. But it was enough to shatter a belief that had lasted millennia. In a single night, the Milky Way went from mythology to astronomy, from milk to stars. But knowing it was made of stars did not tell anyone what shape it was or how large, or where we were inside it. In the late 18th century, William Herschel, a German-born musician who became one of the greatest observational astronomers in history, attempted to map the galaxy by counting stars in different directions. His method was crude but ingenious. Wherever he saw more stars, the galaxy must extend further. He spent years at the eyepiece, systematically surveying the sky, counting and cataloguing, assisted by his sister Caroline, who was herself a remarkable astronomer. The first woman to discover a comet, the first woman to receive a salary for scientific work in England, and the first woman to be awarded the gold medal of the Royal Astronomical Society. Together, they concluded that the Milky Way was a flattened disk with the sun somewhere near the center. William was right about the shape. He was wrong about our position. Badly wrong. It took another century and a half to correct the error. In the 1920s, an astronomer named Harlow Shapley studied globular clusters, those ancient, dense spheres of stars that orbit in the halo, and noticed that they were not evenly distributed across the sky. They were concentrated in one direction, toward the constellation Sagittarius. Shapley realized that the globular clusters were orbiting the true center of the galaxy, and that the Sun was not at the center at all. It was far out toward the edge, 2/3 of the way from the core to the rim. This was a profound demotion. For centuries, humans had assumed they were at the center of things. First the center of the solar system, then the center of the galaxy. Shapley showed that we were suburban, peripheral, orbiting in a quiet lane far from the action, in a galaxy far larger than anyone had imagined. And then, almost immediately, came an even bigger revelation, and it began with a debate. In 1920, Shapley and another astronomer, Heber Curtis, faced each other in what became known as the Great Debate, a public argument about the size of the universe. Shapley believed the Milky Way was the entire universe. The fuzzy spiral nebulae that astronomers had observed through their telescopes were, he argued, small clouds of gas within our own galaxy. Curtis believed the opposite, that the spiral nebulae were island universes, entire galaxies comparable in size to our own, lying at enormous distances beyond the Milky Way. The two men presented their cases. Neither could prove his position definitively. The question remained open. It was settled 4 years later. In 1924, Edwin Hubble, using the most powerful telescope in the world at the time, the 100-inch Hooker telescope on Mount Wilson in California, resolved individual stars in the Andromeda Nebula. By measuring the brightness of a particular type of variable star called a Cepheid, he calculated the distance. And the distance was enormous, far too large for Andromeda to be inside the Milky Way. It was not a nebula at all. It was another galaxy, a separate island of stars, millions of light years away, comparable in size to our own. Curtis had been right. The universe was vastly, incomprehensibly larger than anyone had imagined. In a single observation, the Milky Way went from being everything to being one of countless billions. One galaxy among hundreds of billions. A single spiral in a cosmos so vast that the distance between galaxies dwarfed the distance between stars by a factor of millions. Every step of this journey, Galileo seeing stars, Herschel mapping the disk, Shapley finding the center, the Great Debate, Hubble discovering other galaxies, was a step away from the assumption that we were special, that we were central, that the universe was built around us. It was not. We are in one galaxy, in one arm, around one star, on one planet, in one quiet corner of a universe that contains more galaxies than there are grains of sand on every beach on Earth. And yet, here we are, looking up, asking questions, building telescopes, and slowly, painstakingly, mapping the thing we are inside. The most ambitious effort to map the Milky Way is happening right now. A spacecraft called Gaia, launched by the European Space Agency in 2013, is orbiting the Sun at a point roughly 1.5 million kilometres from Earth, measuring the positions, motions, distances, and brightness of nearly 2 billion stars. Not thousands, not millions, billions. It measures the position of each star to an accuracy so fine that it could, in principle, detect the width of a human hair from 1,000 kilometers away. With each data release, and there have been several, each one transforming the field, the map becomes sharper, the structure clearer, the motion more detailed. Gaia has revealed stellar streams from shredded galaxies that no one knew existed. It has mapped the warp and wobble of the disk. It has traced the orbits of stars with a precision that was unimaginable a generation ago. It has found evidence of ancient collisions that reshaped the galaxy billions of years ago, hidden in the motion of stars that are still carrying the gravitational memory of those events. We are, for the first time in history, beginning to see the shape of the thing we live inside. Not from the outside, we may never achieve that, but from within, star by star, stream by stream, orbit by orbit. The forest is starting to reveal its outline. The pattern is emerging from the trees, and the galaxy, as always, is stranger than anyone expected. The disk wobbles as it spins, rippling like a spinning plate nudged off balance. One side is thicker than the other. The spiral arms are uneven in brightness and extent. Even the halo is slightly off-center. The Milky Way is not symmetrical. It is not clean. It carries the scars of every collision, every merger, every gravitational tug from every dwarf galaxy that ever passed too close. Its beauty lies not in perfection, but in the opposite. In the quiet, accumulated evidence of 13 billion years of history, written in the motion of stars and the shape of dust, and the faint, patient turning of a disk that has never been still. It is not a clock. It is not a machine. It is a living, breathing, evolving structure, and you are part of it. The Milky Way is not alone. It belongs to a small family of galaxies called the Local Group, a loose collection of more than 50 galaxies drifting together through space, bound not by proximity, but by gravity. Most of them are small, faint dwarf galaxies, dim ellipticals, and ghostly systems made almost entirely of dark matter, some so sparse that they contain fewer stars than a single globular cluster. You could look directly at several of them through a telescope and barely notice they were there. Some are so faint and so diffuse that they were only discovered in the last few years, hiding in the glare of the Milky Way itself. Ultra-faint dwarfs with only a few thousand stars held together more by their dark matter halos than by any visible structure. They are the ghosts of the Local Group, barely there, but gravitationally real. But two members of the family dominate, the Milky Way and Andromeda, the two great spirals, each with their own entourage of satellite galaxies orbiting around them like moons around planets. Between them, they account for most of the mass, most of the stars, and most of the gravitational influence in the Local Group. Everything else orbits them or drifts between them, or is slowly being pulled toward one or the other. There is a third member worth knowing about. The Triangulum Galaxy, also called M33, is the third largest galaxy in the Local Group. It is a smaller, looser spiral than either the Milky Way or Andromeda, and it may itself be a satellite of Andromeda, bound to the larger galaxy and destined to be swept up in the same collision that awaits us all. When Andromeda and the Milky Way merge, Triangulum may be drawn in too, a third dancer joining the slow gravitational waltz, its stars scattered into the expanding debris of a merger already hundreds of millions of years old. The Local Group spans roughly 10 million light-years. That is an almost incomprehensible distance, but by cosmic standards, it is a neighborhood, a small one. Beyond it lies the Virgo supercluster, a vast web of galaxy groups and clusters stretching across 100 million light-years. And beyond that, the Laniakea supercluster. a structure so large that the Virgo supercluster is merely one lobe of it. The name Laniakea comes from Hawaiian. It means immeasurable heaven. It was identified in 2014 by a team led by astronomer Brent Tully, who mapped the gravitational flows of thousands of galaxies and found that they were all drifting slowly toward a single region of space, the Great Attractor, an enormous concentration of mass hidden behind the plane of the Milky Way, pulling everything in the local universe toward it with a gravity we can measure but cannot fully explain. But tonight, we are staying close to home, because even within the local group, there is more than enough to fill a lifetime of wonder. The two most visible satellite galaxies of the Milky Way are the large and small Magellanic Clouds. If you have ever been in the southern hemisphere on a clear night, you may have seen them, two bright, hazy patches in the sky, looking almost like detached pieces of the Milky Way itself. They are named after Ferdinand Magellan, whose crew recorded them during their circumnavigation of the globe in 1519. But they had been observed and named by southern hemisphere cultures for thousands of years before any Europeans saw them. The Aboriginal Australians knew them. The Polynesians used them for navigation. The South African San people told stories about them. Magellan merely brought them to European attention. The name stuck. The knowledge that preceded it by millennia did not. They are small galaxies in their own right, each containing billions of stars. They are close, by galactic standards, roughly 160,000 light-years for the large cloud, 200,000 for the small. The Large Magellanic Cloud contains one of the most spectacular stellar nurseries in the nearby universe. The Tarantula Nebula, a region of star formations so intense and so luminous that if it were as close to Earth as the Orion Nebula, it would cast visible shadows on the ground at night. The stars forming inside it are among the most massive known, some over 100 times the mass of the Sun, burning so fiercely that their lives will be measured in millions of years rather than billions. For a long time, astronomers assumed the Magellanic Clouds were long-standing companions, orbiting the Milky Way for billions of years like faithful attendants. But recent measurements of their velocity suggest something different. They may be newcomers, visitors on their first close approach, captured only recently by the Milky Way's gravity, falling inward from the depths of intergalactic space. If true, what we are witnessing is not a stable arrangement, but a first encounter. The beginning of a relationship that may end over billions of years, with the Magellanic Clouds being torn apart and absorbed, their stars scattered into the halo like all the dwarf galaxies that came before them. There is already evidence of this process beginning. Trailing behind the Magellanic Clouds is a vast ribbon of hydrogen gas called the Magellanic Stream, a structure stretching over hundreds of thousands of light-years, invisible to the eye but glowing in radio wavelengths. This gas was pulled away from the clouds by tidal forces as they passed close to each other and to the Milky Way. It is a thread of material being drawn out of two galaxies by a third, a long, trailing whisper of motion and loss. And ahead of the clouds, leading their path, is another structure, the leading arm, a bridge of gas that extends forward, pulled toward the Milky Way's disk by the galaxy's gravity, reaching out like a hand. Material from the Magellanic Clouds is already falling into the Milky Way. The absorption has begun. The stream may, one day, fuel a new generation of stars in the Milky Way's disk. The cloud's own stars may eventually join the halo. Nothing in the local group is permanent. Everything is in motion, falling inward, spiraling together, exchanging material in a slow gravitational conversation that has been going on since the universe was young. And this brings us, gently, to the future. The Milky Way is not what it used to be, and it is not what it will become. Star formation, the process that creates new suns from collapsing clouds of gas, is slowing down. It peaked billions of years ago when the galaxy was younger and its gas supply was richer. Back then, the Milky Way was a more violent, more active place. Stars were forming at a rate perhaps 10 or 20 times higher than today. Supernovae were more frequent. The interstellar medium was denser, more turbulent, more fertile. The galaxy glowed brighter, bluer, hotter, lit by the short-lived massive stars that dominated its youth. Now, the pace has eased. There is still gas available. The galaxy is not empty, but much of it has been heated, dispersed, or locked into forms that resist. Collapse. New stars are still being born. The Milky Way produces roughly 3 new solar masses of stars per year, which means somewhere in the galaxy, right now, in a dark cloud you cannot see, gas is collapsing and a new star is igniting, but the rate is a fraction of what it once was. The Milky Way is entering what you might call its middle age. Not dying, not fading, just settling. A mature spiral, glowing gently, still creating, but no longer in a hurry. The galaxy breathes as it ages. Gas heated by supernovae and stellar winds rises out of the disk, climbing into the halo in vast columns and bubbles. Up there, far from the plane of the stars, it cools, condenses, and over millions of years it rains back down, rejoining the disk, mixing with existing material and contributing to the slow, patient cycle of star formation. Astronomers call this the Galactic Fountain. It is a quiet respiration, an exhale and an inhale that redistributes matter and energy across the galaxy's structure. The Milky Way does not just spin, it circulates, it breathes. Heavy elements forged in the depths of stars are carried upward, spread through the halo, and return to the disk enriched and redistributed. The fountain stirs the galaxy, prevents stagnation, and ensures that the chemistry of each generation of stars is different from the last. And there is another source of fuel. The galaxy does not exist in a vacuum. Thin streams of gas flow inward from the intergalactic medium. The faint, thread-like web of matter that connects galaxies across the cosmos. This cosmic web is not a metaphor. It is a physical structure. Vast filaments of dark matter and gas stretching between galaxy clusters, mapped by astronomers using the light of distant quasars that illuminates the hydrogen along the way. The Milky Way sits at a node in this web, and cold gas flows inward along the filaments, providing the raw material for new generations of stars. The galaxy is not a closed system. It drinks from distant reservoirs nourished by threads of matter that have been drifting through the universe since the earliest epochs. Even now, the galaxy is being fed, but eventually the fuel will run low. The gas will be used up or heated beyond the point where it can collapse. Star formation will slow to a trickle, then stop. The last stars to form will be small, red, and dim, the kind that burn their hydrogen so slowly they can last for trillions of years. Long after the sun has died, long after most of the galaxy's stars have faded into white dwarfs and black dwarfs and cold, invisible remnants, these tiny red stars will still be burning. The last lights in a darkening galaxy. Some of them may burn for 10 trillion years or more, 700 times the current age of the universe. They will be the final witnesses to the Milky Way's existence, still glowing when almost everything else has gone dark. But before that, long before that, something else will happen. Andromeda will arrive. We began tonight with this, and now we return to it, because it is the defining event in the Milky Way's future. In roughly 4.5 billion years, the two galaxies will meet. The collision will take hundreds of millions of years. The spirals will distort, stretch, and eventually dissolve. Stars will not collide. The distances are too vast, but orbits will be scrambled. Some stars will be flung into intergalactic space. Others will be drawn inward toward the merged center. Gas clouds will collide, compress, and trigger a burst of new star formation. One last blaze of creation before the fuel is exhausted. The two supermassive black holes, ours and Andromeda's, will spiral toward each other, drawn by gravity, losing energy through gravitational waves that will ripple outward through the fabric of space-time. Over millions of years, they will draw closer and closer, orbiting faster and faster until they merge into a single, larger black hole at the center of the new galaxy. The merger itself will produce a burst of gravitational waves so powerful that if anyone were there to detect them, they would be unmistakable. A ringing in the structure of space itself. What emerges from the other side will not be a spiral. It will be an elliptical galaxy, a vast, smooth, golden cloud of old stars, slowly cooling, slowly fading, drifting through a universe that is itself expanding and cooling. The new galaxy will have no spiral arms, no density waves, no rolling pattern of stellar birth and death. It will be quiet, enormous, and very, very old. No one will be there to name it. The sun will have died long before the merger is complete, swelling into a red giant that engulfs Mercury and Venus and scorches the Earth to bare rock, before shedding its outer layers and collapsing into a white dwarf the size of the Earth but with the mass of a star. Whatever remains of our planet will be a cinder, orbiting a cooling ember in a galaxy that no longer exists. But that is billions of years away. And tonight, none of it matters. Tonight, the Milky Way is here, whole, turning. 100 billion stars arranged in a warped, barred, peanut-cored, halo-wrapped spiral that has been assembling itself from the wreckage of smaller galaxies for 13 billion years. Its disk wobbles. Its arms are illusions. Its center is a labyrinth anchored by a sleeping black hole. Its halo is full of ghosts, the scattered remains of worlds that were consumed long ago. Its mass is mostly invisible. Its older stars predate its own structure. Its younger stars are being born right now in dark clouds that you cannot see, collapsing slowly under the weight of their own gravity, igniting one by one in the silence. And you are inside it, 2/3 of the way out from the center, in a quiet spur between two larger arms, orbiting a yellow star that has about 5 billion years of fuel left. You are moving at 828,000 kilometers per hour and you cannot feel it. You are made of atoms that were forged in stars that died before the sun existed. The iron in your blood came from a supernova. The gold in the earth beneath you came from the collision of two neutron stars. The hydrogen in the water in your body has been drifting through the universe since the first few minutes after the Big Bang. The calcium in your bones, the carbon in your cells, the phosphorus in your DNA. All of it passed through at least one star. Some of it passed through several. You are not merely inside the galaxy, you are made of it. You are the galaxy, looking at itself. And now, the stars begin to dim behind your thoughts. The numbers fade. The distances lose their edges. The black hole at the center turns slowly in its silence, and the halo stars drift on their ancient paths, and the rogue planets wander in the dark between suns that will never know they are there. The Magellanic clouds trail their long ribbons of gas across the southern sky. The Methuselah star burns on in Libra, patient and dim. Somewhere in the Orion spur, a cloud of hydrogen is beginning to collapse. And in a few 100,000 years, a new star will ignite, and no one will be there to name it. And it will not matter, because the galaxy does not need an audience. It has been doing this for 13 billion years, and it will go on doing it for billions more. You don't need to hold any of it. You don't need to remember it. It will all be here in the morning. The spiral will still be turning. The black hole will still be silent. The dark matter will still be holding everything in place. The Milky Way is not going anywhere tonight. Sleep well.